Why do some video games and programs based on C++ crash? Usually because of the wrong use of memory. Today, we enter one of the most important concepts in C++, something every game developer using Unreal Engine must eventually understand to avoid the program or game from crashing. So far, we've covered variables, functions, arrays, and strings. Today, we talk about pointers and memory. A pointer is simply a variable that stores a memory address, not a number in your game, not a character, not a boolean. A pointer stores where something lives in memory. Think of your RAM like a huge neighborhood full of tiny houses. Every variable you create lives inside one of these houses. A pointer does not hold the value inside the house. It holds the address of the house. Why does it matter? Because in C++ and especially in Unreal Engine, we often want to work with data without copying it. Pointers let us access and modify things directly. They give us control, speed, and flexibility. Unreal Engine uses pointers everywhere. Actors, components, textures, animations, you name it. So learning pointers now will save you countless hours later. But what you learn today not only applies to Unreal, but to any efficient program you will create using C++. Welcome to the Game Creator Accelerator. I am Tony Munoz. Like, subscribe, comment, share, and tap that bell. Each week, you will get Unreal tutorials, practical strategies, a clear methodology, and inspiration to build your game career. Worry your responsibilities make it impossible. Visit Woolen.com to learn more about the Game Creator Accelerator Lifetime Mentorship. And let's book a one-on-one to see how it can help you. Link is in the description. Now, let's get started. There are two key symbols when talking about pointers. First is the ampersand, the address of operator. When you write ampersand variable, you are asking, where is this stored in memory? For example, let's remove this line. Let's write integer x equals 10 and integer pointer equals ampersand x. Here, pointer does not contain 10. It contains the address of x. Remember what I mentioned about the house, the address of the house and what is inside the house. Next, we have the asterisk, which is the dereference operator. When you write asterisk pointer, you are saying, go to that address and give me what is inside. In other words, you are telling, go to the address of the house and now tell me what is inside the house. Let's present this with some couts. First, the value of x. And I'm going to repeat this 4 times to present the different other values. Now the ampersand x, the value of the pointer, and the dereference of the pointer. And run. Here you can see first the value of x that we assigned at the beginning is 10. The ampersand x, which is the address of this x, where the x is safe, you can see this entire number. This is the address in memory for my computer. Then we see the pointer, but because we didn't dereference the pointer, he's just aiming to the same address of memory. But if we decided now I want to dereference the pointer, which means give me what is inside that address or give me what is inside that house, then we get again the 10. What you got to take from this is that the ampersand gives the address. And then you're using that address to access the value inside. In our previous episodes, when we talk about pass by reference, we allowed a function to modify a variable directly. Pointers are another way to get that kind of power and control. In these simple lines of codes, we already covered 2 important concepts, which are related to the use of the ampersand and the asterisk of operator. The ampersand is the address of operator and the asterisk is the dereference operator. Now let's move on to pointers and arrays. You already saw arrays in previous episodes. Here is something cool. The name of an array often behaves like a pointer to its first element. Let's create a code here. Let's create an array of integers called enemies of the size 3, and the values are 10, 20, and 30. Standard cout is going to present enemies. Let's use another end of line and another cout, and now we'll use the ampersand enemies on the position 0, end of line. I forgot to add the cout here, so let's make things a little bit simpler. Using namespace standard. Now I don't need to use this standard here or here. What do you think this will print and how will be different to this one? Well, let's try it. There is no difference. The first one will give you the address where the array it is located in memory. And the address of the first element of the array is exactly the same address of the array in memory. Another way of presenting the address of enemies in memory is, let's say, integer pointer, declare it as ptr, which is usually the way we define pointers, enemies. Now let's go to the cout, dereference, and line. Let's do another cout, dereference, ptr plus 1, end of line, and cout, ptr plus 2, end of line. So what do you think is going to happen? Let's play it. Because we define here a pointer to work with enemies and declare it with this asterisk at the beginning, now I can dereference the values inside this array. By default, the first value of the first position on the array is the position 0. And for the others, position 1 and position 2, I just have to add 1 to the value of the pointer and then dereference it. And that's why we have here 10, 20, and 30. Refreshing, pointer just point to this address, but because we use the asterisk to dereference, then we get what is inside that address. By default will be the position 0. And by adding pointer plus 1 or plus 2, we get to the other elements inside the array. And because we use also the dereference, then we got that value. Let's do something more interesting. Let's copy all this, paste it at the bottom, and let's remove the dereference and run. And here you have the position in memory of the values of the array. And you can see that the position of 10 is this one, is this at the beginning. This is the position of the 20, and this is the address, or the address, not the position, is the address of the last one, of the 30. We will not go too deep into pointers arithmetic today, but I want you to see that arrays and pointers are related. Now let's talk about dynamic memory. Up to now, our variables and arrays had fixed sizes known at compile time. But sometimes in games, you do not know how many enemies, bullets, or objects you need until the game is running. That's when dynamic memory comes in. The word new asks the system to give you memory while the program is running. Let's go to code. Integer pointer, health pointer, equal new integer. This will allocate a space for one integer. And now we can use that health pointer using the dereference to assign a value of, let's say, 100. And if we present this out, health pointer, it will print 100. Let's test it. Here you have it, 100. We did not write integer health, which is what we've been doing so far. We ask for an integer somewhere in memory and we got a pointer to it. When we finish using that memory, we also have to release it. And the way to do it is delete health pointer. And then health pointer equals to null pointer. This will reset the pointer. And null pointer means this pointer is not pointing anywhere valid. What is important or maybe essential with dynamic memory is that once you use it, you need to delete it. You need to use these two lines of code. And that's one of the tricky parts of C++. It is a very useful tool, but you need to be careful. Now let's create dynamic arrays. Let's start by asking the user how many enemies we're going to use. So cout how many enemies. Cin enemy count. Now let's create our dynamic array. Integer asterisk enemy health new integer enemy count. This will create a dynamic array. And now let's initialize all enemies to 100 health. Now we're going to refresh some knowledge. We're going to use a for integer I equals 0 while I is less than enemy count, I++, enemy health, in the position I will be 100. Now let's test it. Okay, how many enemies? Let's say 5 enemies and enter. Here we did not know enemy count at compile time. We ask for a block of enemy count integers when the game is running. The array already filled all these positions with 100, and we can operate and do different things. But once we finish, as I mentioned for the previous case, we need to release this memory. Let me make a note about release memory. To release memory of an array, we use delete brackets enemy health. Remember that enemy health was defined as an array of integers. That's why we're using these brackets here. And then enemy health null pointer. Now, what are the common pointer pitfalls? Pointers are powerful, but if we're careless, they can break our program. The usual problem that we find in C++ is memory leaks. A memory leak happens when you use a new, like this one or this one, but you forget to delete. If you have this same code, but you remove this section, then you are creating a memory leak, which will eventually crash your game or your program. Let me present you another type of examples. Let's say that you create a function called void create enemies. And this function, the first thing it does is creating the enemy health using dynamic memory. So it will be integer 100. And then you do some things here, but you forget delete enemy health at the end. If create enemies is called many times and we never called it delete, the program keeps taking memory and never giving it back. In a long game session, this can slow down the system until the game crashes. So rule, if you use new, make sure there is a matching delete or delete brackets. Let me remove this error of nature. Another type of usual errors is the dangling pointers. A dangling pointer is a pointer that still holds an address, but the data at the address has been freed or is gone. An example, integer pointer, new integer. Now, to the pointer, we are going to assign, let's say, 42. We are trying to we release the memory, but we try to access what is there. This will create, let's put it, danger, undefined behavior. After the delete pointer, the memory no longer belongs to us. So, reading or writing through pointer is asking for a random buggy behavior, because in that new address could be anything else. That's why, to avoid that, you use the delete pointer, but then pointer equals null pointer. You need to do these 2 lines of code. The other type of error that sometimes happens is the double delete. So people try to do something like this. They try to delete and delete again. This can also crash your program. Again, setting the pointer to null pointer after deleting immediately helps a lot. That is why when you use dynamic memory, you usually create the pointer and immediately after that line, you create the delete and the pointer to null pointer. That way, you avoid the mistake of, I forget to write these other lines of code. Once you have that structure, then you put in the middle of them the rest of the code that you need. It's a good practice. Allow me to remove this section and talk about, let's connecting to what we learned before. In previous episodes, we learned passing parameters by value, which makes a copy. Passing parameters by reference, which lets a function modify the original variable. Pointers give us another way to provide access to data without copying it. For example, here is a function that updates a health value using a pointer. Void apply damage integer, creating a pointer integer damage. And to the value inside health pointer, we are going to subtract the second parameter, which is the damage. Pretty straightforward. Now let's call this function inside the main. Close this. Let's say integer health is equal to 100. And now apply damage and percent health and 20. And let's present the values, health and line. Let's run it and explain. Oh, there was an error. When you find this error that says apply damage identifier not found, it is a stupid error that I do sometimes in C++, and it's because you are calling apply damage from the integer main, but the compiler doesn't identify where is the apply damage because it goes in order, and he tries to run the apply damage, but he didn't find it before. So the solution is copy the apply damage to the top and then run. Now let's explain what is happening here. Inside the main function, we call apply damage ampersand health and 20. Ampersand health gives us the address of health. Inside the function apply damage, we use the health pointer to change the value inside that address. We take that value and we subtract damage. Asterisk health pointer is the actual health value. This is similar in spirit to passing by reference, but using pointers give us more flexibility, especially when we work with dynamic memory and objects created with new. In the case of Unreal Engine, we use these ideas everywhere. You will see pointers to actors, components, widgets, and more. So getting comfortable with this now is a big step forward. To summarize what we learned today, first, a pointer is a variable that stores a memory address. The ampersand gives you the address of a variable. Asterisk lets you access the value at that address. New allocates memory during runtime. Delete and delete brackets free that memory. And the common mistakes to avoid are memory leaks, using new without delete, dangling pointers, using a pointer after deleting its memory, and the double delete, deleting the same pointer twice. If pointers feels weird, that is totally normal. Every C++ programmer struggles at first. But if you rewatch this episode, type the examples and play with them, you will cross that bridge much faster than you think. In the next episodes, we will keep building on this and move closer to how these concepts appear when we work with classes and eventually with Unreal Engine and real game code. Like, subscribe, ring the bell, and comment about this episode. Did it help you understand pointers? And remember to visit Wooden.com to learn more about the Game Creator Accelerator Lifetime Mentorship Program. And let's have a chat if you want to build a solid career in video games one step at a time. Until next time, keep creating, keep sharing, and most importantly, keep dreaming big. I'll see you soon, my fellow creators.